Hey everyone, this is Team 13, and this is our final report on our project Sentiment Analysis based on movie reviews.
So, a little bit of a background and problem definition. With the rise of social media and online platforms, people have been expressing their opinions and sharing their experiences in various ways. One popular way is through movie reviews. The ability to accurately analyze and understand the sentiment of movie reviews is important for various applications such as marketing and feedback analysis. In particular, sentiment analysis of movie reviews can be useful for filmmakers, movie studios, and online streaming services to understand the public's reactions to their movies and to make informed decisions about future productions. One dataset that is commonly used for sentiment analysis of movie reviews is the IMDb dataset of 50,000 movie reviews, and this is the dataset we decided to use as it has labels on positive and negative for each movie review. Uh, so take a little attention to this graph on this slide right here. It talks about how each movie review length is 800 characters, and it shows the frequencies of these movie review lengths. Another visualization here shows the popularity of each word in the movie reviews, and here's the ranking of these popularities.
So, in terms of methods, some methods considered for unsupervised and supervised learning is given the many unsupervised and supervised methods within the areas of machine learning and deep learning, K clustering, support vector machines, Gaussian mixture models, and of course, deep neural networks. Serious consideration was needed to choose appropriate methods. Fundamentally, sentiment analysis is a supervised classification problem. The goal of sentiment analysis is to predict which class a given text input belongs to, either positive, negative sentiment. And because movie reviews and text in general is considered to be sequential data, as a sentence is an organized sequence of words, RNN was used. So, a high level overview of our supervised machine learning method is that we use an LSTM architecture. This processes inputs sequentially, similar to vanilla RNNs, but it avoids the vanishing gradient. This maintains a long term cell state and also maintains a short term hidden states and to learn appropriate dependencies. LSTM units are connected horizontally in order to process the input at each given timestamp. And so, for example, as a word at a position in a sentence, or for example, the price of a stock on a given day. Ultimately, the output at the final timestamp, or in this case, the final state, is what provides a prediction of sentiment classification and is what is seen in the results. So, in terms of supervised machine learning, the LSTM architecture we can go layer by layer. An LSTM unit has 4 layers, and the first two are pretty much used to update the long term cell state, while the last 2 layers are used to update the short term hidden state. The first layer, sigmoid, determines what long term information should be maintained or what long term information should be forgotten. The next 2 layers, sigmoid and tanh, determine what information and how much should be added to the long term cell state. And the final sigmoid and tanh combination, they update the short-term hidden state. In this case, the overarching idea is that through gradient descent, the parameters of each of these layers will be learned such that the model can learn relevant long-term dependencies and it can avoid those vanishing or exploding gradient dilemma. And since the weight and parameters of the model do not directly affect the cell state, uh, but rather they affect the cell state indirectly through different gates.
So, for our project, we also used unsupervised machine learning. We used GloVe text embeddings, and our goal was to map each word in the vocabulary to a vector in a high dimensional space so that the information in a word can be accurately encapsulated or represented in numerical form. If the number of dimensions used was less than 4, then we would see that similar words, such as articles like a and the, would cluster together in space. Embedding weights can be learned via training, typically using gradient descent, but this can be time consuming. Instead, we utilized pre-trained embeddings, such as GLOVE, which provides a numerical representation of hundreds of thousands of English words and sends the embeddings as inputs into the LSTM. This is a general theme in machine learning and deep learning. Unsupervised methods are used to cluster the data so that inputs to a supervised learning model are organized and represented appropriately. So a little bit about our final results. This table, this visualization above, shows the results of the various trials with different LSTM units and learning rates. The validation accuracy is reflected in the final column, and as we can see, the validation accuracy was highest in trial 1, with a learning rate of 0.001, and the LSTM units in this case were 128.
And in this visualization, the x and y axes are the hyperparameters. These are the learning rates and the LSTM units respectively. These were tuned, and the values inside of each box represents the accuracy, and each box represents the trial. This visualization shows a comparison between the accuracies in each of the trials, specifically the visualization on the right. And this visualization on the left illustrates how different learning rates can result in different accuracies, while the visualization on the right shows how the number of LSTM units were tuned overall, and how this resulted in a different accuracy for our results at the end. And as you can see, these are some of our references that were used.